Okay, so we have a nuclear physics practice final exam. Let's get right into it. Number one, assume a nucleus has a radius r equals r naught a to the 1/3, and r naught is equal to 1.20 fm. Okay, so estimate the radius of lead 208. So for this is a nuclear size and density problem, so we want to estimate the radius of lead 208. So we're going to use the formula r equals r naught a to the 1/3. R equals 1.20 fm times 208 to the 1/3, and that's going to wind up giving us our r is approximately 7.1 fm, or femtometers. Okay, and I'm going to go pretty quickly through this. You have the setups, some of the computation and whatnot. I'll gloss over just because the setups are there. Okay, and forgive me if I misspeak. Part B, estimate the average nuclear density in nucleons per FM cubed. So average nuclear density, we're dealing with volume here, 4/3 pi r cubed volume of sphere. We're going to use r as r naught a to the 1/3. So for V, this is going to be V equals 4/3 pi r naught cubed times A. And so our density, that's going to be rho equals A over V. That's going to be A over 4/3 pi r naught cubed A. So rho is 1 over 4/3 pi times 1.20 to the third. And we can estimate this. Rho is about 0.14 nucleons per fm cubed. C, explain why the approximately constant nuclear density suggests saturation of the nuclear force. So here's our interpretation for letter C. So we could say, since density is approximately constant for many nuclei, each nucleon only strongly interacts with nearby nucleons, not all nucleons in the nucleus. So this is called saturation of the nuclear force. Okay, so that takes care of number one. We can move along to number two. Okay, so number two. All right, we have some calculus in number two. So number two, it's binding energy. So we have here the binding energy is modeled by this B of AZ equals this whole thing. I'm not going to say it out loud. It's long. Oh, that's an A to the 1/3. That's A sub A. And that's a delta. I apologize for not drawing the delta well. And then we have our coefficients here, respective for volume, for surface, for Coulomb, and for asymmetry, rather, respectively. Asymmetry, columns, surface, and your volume. And we're going to ignore pairing for this problem. For part A, for a fixed A, derive the approximate most stable value of Z. So we're going to use this is basically semi-empirical mass formula problem. For part A, we're going to ignore pairing. So we're going to have B of AZ equals, from what was given, A sub VA minus A sub S A to the 2/3 minus A sub C quantity Z minus Z times the quantity Z minus 1 over A to the 1/3 minus A sub A quantity A minus 2Z squared over A. So for a fixed A, we maximize B with respect to Z. So the Z-dependent portion is going to be the following. Our B of Z is approximately negative A sub C Z squared over A to the 1/3 minus A sub A times the quantity A minus 2Z squared over A. We're going to differentiate with respect to Z. dB dZ, that's going to give you negative 2A sub C Z over A to the 1/3 plus 4A sub A times A minus 2Z over A. We're going to set this equal to 0 because we want to derive the approximate most stable value of Z. So set it equal to 0. And now we're just going to factor, and after factoring, we're just going to do the algebra here, some arithmetic here, algebra, and z is isolated at 2a sub a over 4a sub a plus a sub c, a to the 2/3, or a over 2 plus, this is a sub c over 2, sorry about that, a sub a, so that's a 2a sub a times a to the 2/3. Okay, so you could have this or this for part A. So that's the answer for part A. For part B, we're going to estimate the most stable z for A equals 100, and z being the number of protons here. So for letter B, for A equals 100, all we have to do, this is a to the 2/3, that's 100 to the 2/3 equals 21.5. We're going to use the formula we derived in part A, and we're just going to substitute values that were given and what we just derived right here. Substitute that into the z formula. We'll use this one, and we wind up getting z is approximately 43. Okay, so part C, let's see here. Explain physically why stable heavy nuclei have n is greater than z. Okay, so here we go here. Protons, we could say protons repel each other electrically. So as z grows, Coulomb repulsion becomes stronger. Extra neutrons add attractive nuclear binding without adding Coulomb repulsion. So heavy stable nuclei need more neutrons than protons. Okay, so that takes care of letter C, and now we can move into number 3, because that was 2A, B, and C. Okay, sorry about that. Moving along into number 3. Okay, so number 3, consider a single neutron outside a closed shell curve. I'm sorry, a closed shell core. Okay. The neutron occupies the orbital, that's 1f 7/2. And what we want to do here is we want to state the orbital angular momentum, the spin, and the total angular momentum. Okay, so part A, this is a nuclear shell model problem. So the neutron occupies 1 7/2. Okay, so the values of our angular momentum, orbital angular momentum, our spin, and our total angular momentum, respectively, is what we want. The letter F is going to mean that our orbital angular momentum is equal to 3. And a neutron has intrinsic spin, S equals 1/2, and the subscript gives J equals 7/2, the total angular momentum. So we wind up with the orbital angular momentum is 3, the spin 1/2, and the total angular momentum is 7/2. Okay, part B, determine the parity of the nuclear ground state. The parity here, it's going to be a negative. So the state has negative parity for that, that pi equals minus, parity equals negative. Since our orbital angular momentum is 3, our parity here, that pi equals that -1 to the orbital angular momentum. That comes out to a -1. So negative parity is the state. That's the work up there. And letter C, if the core has a spin parity, this is 0 plus, give the expected total ground state spin parity. Okay, so if the core, what we could say here, total ground state spin parity, the core is 0 plus. So the total spin parity comes from the valence neutron. Okay, so right here, we're going to get that 7/2 negative, and that's it for part C. Okay, so let's see here. Part D, explain qualitatively why spin-orbit coupling is essential for nuclear magic numbers. Part D, spin-orbit coupling matters. So without strong spin-orbit coupling, the shell gaps would not occur at the observed nuclear magic numbers, and spin-orbit coupling levels with the following. So our total angular momentum equals orbital angular momentum plus 1/2, and total angular momentum equals orbital angular momentum minus 1/2 by a large amount, creating the observed shell closures. Okay, so that's it for number 3, and I apologize if I misspeak at any time. Sometimes I read too fast, which is probably not a good thing, but I'm just trying to get you through this so you have this as a reference for extra problems to study for if you need them. Okay, so let's see number 4. Okay, so you have X. So a heavy nucleus undergoes alpha decay, and this is what we're given in relation to that that X with mass number A and atomic number. Okay, so suppose the atomic masses are given as that M of X is this, M of Y is this, M of alpha is that. For part A, compute the Q value in MeV. That's mega electron volts. This is alpha decay and Q value problem. So here's what we were given in regards to that relationship, given up here. And now our Q value, our Q is going to be bracket M of X minus M of Y minus M of alpha, close bracket again, times C squared. So we're going to plug in these values, factor out the U. We're going to wind up with Q equals 0.0052 U times C squared. Okay, and using here 1 UC squared equals 931.5 mega electron volts. Substitute in here Q equals 0.0052 times that 931.5. We get Q is approximately 4.84 mega electron volts. Okay, moving along to part B. Explain why a positive Q value is not enough to guarantee a short half-life. So here's part B. What we could say is even if the decay releases energy, the alpha particle must escape through the Coulomb barrier. If the barrier is wide or high, tunneling probability is small, so the half-life can still be long. And for part C, describe the role of quantum tunneling in alpha decay. So here's part C. Classically, the alpha particle does not have enough energy to climb over the Coulomb barrier, and quantum mechanically, it has a finite probability of tunneling through the barrier. The decay rate depends strongly on that tunneling probability. Okay, so that's A, B, and C for number 4. So we can move along now to number 5. Okay, so for number 5, so we have a nucleus undergoes beta decay from an initial state, J sub I pi equals 3 plus to a final state, J sub F pi equals 2 plus. Okay, that's J sub F pi equals 2 plus. Part A, determine the value of the change in J and whether delta J and whether parity changes. So this is a beta decay selection rules problem. So our initial amounts and our final amounts were given. Our delta J and parity are, well, our delta J is going to be the absolute value of this 3 minus 2. That gives you 1. Both states have positive parity. So technically there is no parity change. So delta J is positive 1, no parity change in this situation. Part B, is this transition allowed, first forbidden, or highly forbidden? Oh, so for part B is our classification. Our allowed beta decay has delta J equals 0, or plus minus 1 and plus minus 1. with no parity change, except 0 going to 0 is not allowed for gamma teller. So here our delta J is 1, and parity does not change. So this is an allowed transition. So yes, this is allowed beta decay. Part C, would you expect the decay to be relatively fast or slow compared with a strongly forbidden beta decay? Explain. So fast or slow? So allowed beta decays are generally faster than forbidden beta decays because they require less angular momentum transfer. So relatively fast compared with strongly forbidden beta decay. Okay, so that is number 5. Let's move along to number 6. Okay, so number 6, consider a heavy nucleus with Z equals 92, A equals 236. The competition between Coulomb repulsion and surface tension can be estimated using the facility parameter. This is X is approximately Z squared over 50A. Part A, calculate X. So this is a liquid drop model and fission problem. We're given Z equals 92, A is 236. We can use X in this situation, approximately Z squared over 50A, and we just substitute our values from what was given, and our X value is about 0.72. For part B, we want to interpret part A's result physically. So for part B, take a look at X. 0.72 is less than 1. So since X is less than 1, surface tension still stabilizes the nucleus against immediate fission. But X is fairly large, meaning Coulomb repulsion is significant and the nucleus is close to being fissionable. Okay. C, explain why neutron absorption can induce fission even if the original nucleus is not spontaneously fissioning rapidly. So, part C, absorbing a neutron forms an excited compound nucleus. The excitation energy may push the nucleus over the fission barrier, allowing it to split. Part D, describe why fission fragments tend to be neutron rich. So here's part D. So heavy nuclei are neutron rich before the fission. The fragments inherit much of that neutron excess. Also, neutron-rich fragments reduce Coulomb repulsion compared with having too many protons. So there's part D, and that's all for 6. We can move along now to 7. Okay, so 7, an alpha particle with kinetic energy E equals 5.00 MeV scatters from a gold nucleus with Z equals 79. The distance of closest approach in a head-on collision is approximately R sub min 1 over 4 pi epsilon naught times Z sub 1, Z sub 2 times E squared over capital E. And we're going to use this E squared over 4 pi epsilon naught equals 1.44 MeV dot FM. So calculate for part A our R sub min. So this is Rutherford scattering. Take what we're given, and for R sub min, we're just going to substitute Z sub 1, Z sub 2 times 1.44 MeV dot FM over E. So the distance of closest approach, R sub min is 2 times 79 times 1.44, just substituting what we were given, over 5. So R sub min is approximately 45.5 FM. Okay, so here, compare this for part B. Compare this with a typical gold nuclear radius. So for gold, our A is approximately 197. We take R equals 1.20, multiply that by 197 to the 1/3. So R is about 7.0 FM. And if we compare these two, this R sub min, okay, is much larger than the nuclear radius here. So, of R sub AU for gold. Okay, so, part C, explain why Rutherford scattering provided evidence for a compact nucleus. So here we go. Part C, large angle scattering showed that positive charge and mass are concentrated in a tiny central region rather than spread throughout the atom. So that's part C there. That's number 7. Let's move along to number 8. Okay, so number 8, consider we have lowercase a plus capital A go to lowercase b plus capital B. Suppose the Q value is Q equals negative 3.20 MeV. The target A is initially at rest. Let M sub A equals 4U. M sub capital A equals 16U. And here we're given the approximate threshold kinetic energy equal to negative Q times the quantity 1 plus M sub A over M sub capital A. So for part A, compute the threshold energy. So this is a nuclear reaction threshold energy problem. Take what we're given. We're going to use the approximate threshold kinetic energy equation here. Well, approximation rather. So that's going to equal, substituting, that's going to be negative 3.2 times the quantity 1 plus 4 over 16. 3.20 times 1.25 will get 4. So that threshold energy is 4.00 MeV. Part B, explain why the threshold energy is larger than absolute value Q. So B, some kinetic energy must go into conserving momentum. The final products the final products cannot both be at rest in the lab frame because the initial projectile had momentum. Part C, what happens if the incident particle energy is below threshold? Well, we could say this: if the incident energy is below threshold, the reaction cannot occur because there is not enough energy to create the final products while conserving energy and momentum. Okay, so that's number 8. We can go on to number 9. Okay, number 9. Okay, number 9. Number 9, the deuteron has spin parity, and the J to pi equals 1 plus, and is weakly bound. Okay, so let's see what we have here. Explain why the deuteron cannot be pure L equals 0, S equals 0 state. Okay, so deuteron properties problem. Okay, so if L equals 0, S equals 0, then J equals 0. Because the total angular momentum would be J equals L plus S equals 0. However, the deuteron, J equals 1. So it cannot be a pure L equals 0, S equals 0 state because that deuteron, J equals 1. Okay, so part B, what dominant spin and orbital angular momentum configuration describes the deuteron? Okay, all right, so let's see. Dominant configuration. The dominant deuteron state is L equals 0, S equals 1. Okay, so this is a triplet S1 state. So triplet S1 dominant. There's also a smaller triplet D1 component. Okay. All right, so moving along here to letter C. Why does the deuteron have a non-zero quadrupole moment? A non-zero quadrupole moment, for this one, why does it have it? A pure S wave is spherically symmetric and would have 0 quadrupole moment. The observed non-zero quadrupole moment means that deuteron has a small D wave admixture caused by the tensor portion or tensor part of the nuclear force. Okay, so that's part C. And part D, what does the weak binding of the deuteron imply about the range and strength of the nuclear force? So for part D, the weak binding implication, what we could say is the deuteron is only weakly bound. So the nuclear force is strong but short-ranged and just barely binds the neutron-proton system in this channel. Okay. And just as an extra note here, carbon is effective mostly because it has low neutron absorption and decent energy loss per collision. Not necessarily because it is as efficient per collision as hydrogen slash deuterium. Okay, so that's number 9. Moving along to number 10. Okay, so number 10, here we have a single proton is in a d sub 5/2 state. Okay, and let's see, orbital. So d 5/2 orbital outside a closed shell core, and we want to identify the following. Okay, so nuclear magnetic moment. So we're dealing with here our letter D. I'm sorry. So letter D means angular momentum is 2. Orbital angular momentum 2. Subscript gives J equals 5/2. Parity is pi equals -1 to the orbital angular momentum. And that's -1 squared. That's positive. So we wind up getting for our values for orbital angular momentum 2. J is 5/2. And then we get a positive, the parity there, pi equals plus. Okay, so let's see here. Part B, determine the expected spin parity of the nucleus if the core is 0 plus. So nuclear spin parity, if the core is 0 plus, the valence proton determines the total spin parity. So that we have that J pi equals that 5/2 plus. Okay, so C, explain why measured magnetic moments often differ from simple single particle shell model predictions. So for part C, the simple shell model assumes one independent valence nucleon outside an inert core. Real nuclei include configuration, mixing, core polarization, Mason exchange effects, and many body interactions, which shift magnetic moments away from simple predictions. Okay, so that's all for A, B, and C. I apologize if I misspoke there. Okay, so that's 10. Here's 11. 11, fast neutron has kinetic energy about 2 MeV. The thermal neutrons have energies around 0.025 eV. Part A, explain why moderators are used in thermal reactors. So this is more textbook stuff. Number 11, textbook notes stuff. So neutron moderation and reactor physics. So for part A, what we could say, fission neutrons are born fast around MeV energies. Many reactor fuels, especially uranium-235, have larger fission cross sections for thermal neutrons. Moderators slow neutrons down to thermal energies. Okay, part B, why are light nuclei such as hydrogen, deuterium, and carbon effective moderators? So for part B, light nuclei remove a large fraction of neutron kinetic energy per collision because their masses are comparable to the neutron mass. Hydrogen is especially effective because a neutron can transfer a large amount of energy in one collision. C, explain the difference between neutron scattering and neutron absorption in reactor operation. So here's C. This is in 2 parts. So scattering changes the neutron's direction and energy, but does not remove it from the neutron population. Also part of C. Absorption captures the neutron, removing it from the chain reaction unless the absorption causes fission. And for part D, why must a reactor maintain criticality rather than supercriticality? So for part D, a critical reactor has K equals 1, meaning each generation of neutrons produces exactly 1 new generation. A supercritical reactor has K value greater than 1, so neutron population grows. Controlled reactors are kept near critical to maintain steady power rather than runaway growth. And that is very, 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 very super important. Okay. So that's A, B, C, D. That's for number 11. And let's move on to the last one. Number 12, which are also notes / conceptual textbook stuff. Okay, so number 12 in stellar nucleosynthesis, charged particle fusion reactions occur despite strong Coulomb repulsion. For part A, explain the Coulomb barrier problem. So for part A, Coulomb barrier problem, two positively charged nuclei repel each other electrically. At stellar temperatures, their average thermal kinetic energies are often much smaller than the Coulomb barrier height. Part B, describe qualitatively how quantum tunneling enables fusion in stars. Okay, so even if nuclei do not have enough classical energy to overcome the barrier, quantum mechanics gives a finite probability that they can tunnel through it and fuse. Part C, what is the Gamow peak? Part C, the Gamow peak is the energy range where fusion is most likely. It comes from a balance between these two things. One, the Maxwell-Boltzmann distribution, which favors lower energies, and two, the tunneling probability, which favors higher energies. The overlap gives a peak at an intermediate energy. Part D, explain why reaction rates in stars are extremely sensitive to temperature. So here's part D. A small temperature increase gives more particles in the high energy tail of the Maxwell-Boltzmann distribution and greatly increases tunneling probability. Therefore, stellar fusion rates are highly temperature sensitive. And that's all. 12 free response here, and I hope this could help out with review for a nuclear physics exam, just some extra practice. Thank you very much, and have a great day.